So we talked about quantum parallelism, which is different from classical circuit parallelism. When we have n-bit input, then classical parallelism means we can have n, or at most n squared, gates operating simultaneously. N squared because when we have gates with two inputs, any pair of possible inputs, when there are n inputs, it means there are at most n squared gates connected on the first layer. That's polynomial parallelism. Acceleration is a different matter. That's steps, right? But the number of gates that run concurrently, that's polynomial. Here we have a similar thing. We have the Hadamard gates, and they operate concurrently on the qubits, on the ions that are trapped here. Again, n-fold concurrency. As opposed to that, quantum parallelism is exponentially more. Quantum parallelism is because of the linearity. We have a qubit gate, and the input is in a superposition. Then this superposition can be comprised of up to exponentially many basis vectors, right? And that's what the Hadamard gate actually creates. It starts with a simple input state like 0, 0, 0, 0. And after the Hadamard gate, we have a uniform distribution. Every possible qubit value is present in the state with equal complex weight. When we then repeat that, apply some other unitary circuit, then it means that quantum circuit gets applied by linearity to all exponentially many possible input values. So that's the real acceleration, the benefit. The constraint, however, is that this must be unitary gate, and we must be able to represent that gate in polynomial size. Although this U is an exponential size unitary matrix. An example, we consider the Fourier transform. First, the discrete Fourier transform, but now an exponentially many exponential input size vector and exponential output size vector, 2 to the n. And I claim that this is a unitary transformation, unitary matrix of exponential size, but it can be expressed using only polynomially many smaller gates. And this is this mathematical formula which we didn't really verify and calculate, but if you'd believe me, this is just small n tensor product of small n, so polynomial size. Way to express this exponential size unitary Fourier transform using only polynomial. And this is why this slide has the title Fast Quantum Fourier Transform. But again, I want to emphasize there's a fast Fourier transform, which is very well known for hundreds of years. What is the fast Fourier transform? The ordinary Fourier transform, if you have an input vector of size n, and you want to calculate one output, one entry in the output vector, there's this sum, right? You see the sum, n terms, capital N terms. That's O of n to calculate classically, classical sequential algorithm. And to calculate all n output entries, do that n times. So naive algorithm for the classical Fourier transform is n squared. And the fast Fourier transform manages to calculate that in time n log n, which definitely is better, faster, fast Fourier transform. But the acceleration is only from n squared to n log n. Here we're talking about exponential acceleration, right? So that's an entirely different magnitude. So don't confuse the two fasts. And we started talking about quantum phase estimation as a meta problem where the input is a fixed unitary transformation. We'll have to discuss later how to represent that exponential size matrix using only polynomial information. And the input is a vector, state vector, exponential dimension vector, which is promised to be an eigenvector to this. Again, I'll remind you in a minute how we use that setting. It's a strange setting, something to be promised an eigenvector. And the quantum phase estimation problem is to determine the eigenvalue. More precisely, since the eigenvalue is a complex number of magnitude 1, it means we want to determine theta, the real parameter, in the exponent between 0 and 1. Not necessarily exactly, but approximately, and I'm going to say what approximation means in a minute. Then I showed you Peter Shor's hybrid algorithm for factoring integers in polynomial time, polynomial in the length of the integer, using quantum phase estimation as a subroutine. It's a hybrid algorithm because superficially it's a classical randomized algorithm. After the midterm, chapter 5, randomized algorithm, we'll talk more thoroughly about that. You see that here because in item 1, line 1 says pick a random number. Also, this algorithm may error, in which case it has to start over again, picking a random number. This is what we're going to call a Las Vegas algorithm, but more about that after the midterm break. And the goal is to calculate the order of the random integer a modulo x in the case that a is coprime to x. Remember what coprime means. And this is achieved by Shor using this quantum phase estimation. So this is the definition of the order, the least integer k as integer exponent to a, such that a to the k is congruent to 1 modulo x, meaning a to the k minus 1 divisible by x. And how is this related to phase estimation? It's related to phase estimation by considering one particular unitary transform given and fixed these coprime integers a and x. They're supposed to be m-bit integers, so x is less than 2 to the small m. And here we define a unitary transformation, a unitary operator on m qubit states. We defined it on the basis vectors, which are just, binary strings of length m, which we consider as binary encoding of some integer L. And after the transform, the vector is supposed to be a basis vector whose binary encoding is L times A. So basically this is multiplying L by A, but in binary, and it's a linear transform. when L, the input vector, is less than x, we need to define it also when L is greater or equal to x, but still an m-bit integer. And here we just define it to be the identity. And an important first observation is that this transformation is indeed unitary. It is unitary because of our hypothesis, as it occurred as an invariant in Shor's algorithm, that A and X are coprime. This is crucial. Since A and X are coprime, U is a unitary transform. But it's an exponential size unitary transform, right? It happens on m qubit states. Being unitary, we know something about the eigenvalues. They are complex numbers of magnitude 1, so we have this real phase parameter. And we are interested in approximating that phase parameter because the known property of number theoretic property of A modulo X, namely, for example, the order, translate to properties of this unitary matrix, namely that U to the K is equal to the identity matrix, which implies that the phase, the real phase, is actually a rational number, a fraction, where the denominator is R, the order that we're interested in, and the numerator is K for some integer K between 0 and R, corresponding to this unitary matrix having all these possible many eigenvalues: 0, 1 over R, 2 over R, 3 over R, R minus 1 over R in the exponent of e to the 2 pi I k over R. And I told you and asked you to verify, calculate that this is the corresponding normed eigenvector. It's normed because we divide by square root of R. Check that it is normed. Check that when applying U to this, that is basically multiplying this with A, and you see the exponent becomes A to the j plus 1. Do some shift and see this is exactly an eigenvector. Applying U results in a multiple of this vector, that's an eigenvector, multiple given by the eigenvalue. And also check that the sum of all these normed eigenvectors is this particular basis vector. Not 0, 0, 0, 0, as we usually start with Hadamard gate, but 0, 0, 0, 1. And I also explained to you why that is important, because when we have solved the quantum phase estimation problem, then we will use that as a subroutine to Shor's algorithm to determine the order of A in the following way. So we take this unitary transform. We know mathematically these are the eigenvectors. We know mathematically these are the eigenvalues. But we cannot make use of so I'm going, the rest of next 30 minutes, I'm going to show you how describe your quantum circuit for solving the quantum phase estimation problem. But first, suppose we have solved it, how can we make use of that? Because it needs that promise that the input is an eigenvector. How can we invoke the quantum phase estimation circuit? First, we need to prepare such an eigenvector, but this eigenvector is exponentially large, right? Remember again, this sum here, J, exponentially many terms. Also, it involves R, which our goal is to determine R, so we don't even know R. But this is where the quantum parallelism comes into play. Namely, once we have solved the quantum phase estimation problem for one promised eigenvector, that means we will be able to execute that simultaneously for all possible eigenvectors. By linearity, it will output a linear combination of these psi prime vectors. And then we make the measurement. And remember what happens during a measurement in quantum mechanics? The superposition state collapses to one of the eigenvectors. There's no telling which one. Quantum mechanics is intrinsically non-deterministic, random. But that means after having run our quantum phase estimation circuit and then performing a measurement, the result will be an approximation to this fraction k over r for some k. We have no way of telling which k, just some k between 0 and r. But then we do some number theory, and from that, the approximation must be good enough to uniquely identify numerator and denominator, right? But if we have the approximation good enough, then we can do that, and then we can extract r and discard k, because remember, there's no telling which k will be the result of the measurement. And how do we execute this quantum phase estimation circuit later on all eigenvectors simultaneously? That's where our last equation comes in. This is all of eigenvectors simultaneously, right? And it has this very simple form. So we don't need to know r, we don't need to form this exponential size sum or this exponential size sum. We only need to prepare this one very simple initial state, which is basically means all spins are down except for the first atom in the trap, which has spin up. This is easy to prepare, right? Well, in principle, for physicists or engineers, this is still pretty hard, but at least conceptually, this is much easier to prepare, and then mathematics takes care of the rest with linearity, quantum parallelism. So this is how quantum phase estimation problem occurs as a kind of subroutine in Peter Shor's algorithm. Peter Shor's algorithm tries to determine the order, and in order to determine the order, you run this quantum phase estimation circuit that I still haven't shown you yet, because that's what we do in the next 20 minutes. Quantum phase estimation. How do we solve it? It's a meta problem because the input involves quantum circuit U. And in order to solve it, we're going to design another quantum circuit that, of course, involves U. It's kind of like a subroutine, right? Only it's a quantum subroutine to some function parameter. No, here it's a sub-circuit parameter U. And just to give you an expression, what can we do with these sub-circuits U? We can invoke it once, and we know that the result will be an eigenvector, so it will be a multiple e to the 2 pi I theta for the phase that we're interested in. We can also invoke it twice, which means that the resulting eigenvector will be, eigenvalue will be the original one squared. Squared means twice in the exponent, here 2. Or we can even invoke it 3 times, then it's 3 times in the exponent. Or we can invoke it A times, and then B times, and then C times, which means that A plus B plus C is in the exponent. That's what we can do, and that's what we will do, but more generally, in order to solve the quantum phase estimation meta problem. So here's our quantum phase estimation meta circuit, which involves as parameter, as function parameter, subroutine, subcircuit, the given unitary U. And the promised eigenvector m-bit qubit eigenvector to this U. And the output should be an approximation to this phase up to error 2 to the minus n, which means it should be roughly the first n bits after the binary point. But we can only output and input integers, right? As qubit states. So instead, we output, we scale theta, move it the n bits in front of the binary point, and then round it. So here the quantum phase estimation meta circuit makes this subroutine calls to U and to powers of U. It in turn must be unitary. And it outputs an n-bit approximation. And in order to output the n-bit approximation, remember everything must be invertible, reversible. So to this end, we provide an additional n qubit input, which is initialized with 0. And on these qubits, after the calculation, these will contain the desired n qubit approximation to the phase theta. Right? We cannot drop qubits, otherwise it would not be invertible. Like Boolean AND is not invertible because it has 2 inputs and only 1 output. Instead, to make the AND quantum gate, we add another second output defined in a suitable way, then it becomes invertible, and then we can turn it into unitary matrix. That's what happens here. Only here we have n qubit output, so we need an additional dummy input. And that output should be the first n bits after the binary point of theta. Theta is between 0 and 1. Mathematically, this means multiply theta by 2 to the n, shift the real number n bits to the left, then round. This here is round to nearest, right? You can round up, you can round down, and this here is round to nearest. And the result will be an integer, an n-bit integer, and that's supposed to be the output of our quantum phase estimation meta circuit, which we're currently developing. So the goal is to calculate this nearest integer y nearest to theta times 2 to the n, which means that y divided by 2 to the n is an approximation to theta actually up to error 2 to the minus n minus 1, even 1 bit better, but anyway, that's detail. So the quantum phase estimation circuit that we're going to design has m plus n qubit input, m qubit input for the promised eigenvector, n qubit input for the dummy zeros, and m plus n qubit output. It later turns out that n, the approximation error, can be something like 2m. That's sufficient precision. And then at the end, we make this measurement, which determines, in particular here, this y. At least with high probability, because remember, everything in quantum mechanics happens with some intrinsic probability according to this axiom. So here we go. Quantum phase estimation meta circuit. Remember, we want to determine this integer y, n-bit integer. then the approximation error delta is at most 2 to the minus n plus 1 in magnitude. That's our goal. And the first thing we do is apply the Hadamard transform on the n qubit dummy input to 0 so that we can have again full superposition of all possible resulting values y. And then comes the actual quantum phase estimation meta circuit V, which involves U, of course, and the powers of U, the unitary transform we're interested in. Contains actually controlled powers. Remember what controlled means? It means there's one qubit. If that is 0, nothing happens to the others. If that is 1, then something happens to the others. That's a general idea. And here's the definition of V. And here you see why it's controlled. It says if the first qubit is k in binary, then apply u to the kth power to the other m qubits. This is the meaning of this tensor product. This means to the other m qubits apply u not just once, but k times u to the kth power, where k is given by the first n qubits as a parameter. And this means don't change the first n qubits. So this is a sum of controlled powers of u. The first n qubit tell which power of u to apply to the others. That's a nice idea. And we'll do the math in a minute. Oh, actually, I'm gonna skip over the math in a minute, letting you believe that the math works out. But the problem here is, of course, again, that the sum defining V here is exponentially large. So that in order to construct this V, we need to have copies of U, one copy of U, one copy of U squared, which is U times U, one copy of U cubed, U times U times U, and so on up to K. And that's exponentially many copies, right? First, remember, K ranges up to N, capital N, and N, that's 2 to the small n exponentially. So here's the math, which I'm going to skip over. The result in the first n qubits will be our approximation. The other qubits will be eigenvector. And here's a formula for the first n qubits, which is again going to be a superposition, right? And then we apply the inverse quantum Fourier transform. Remember, we discussed the task quantum Fourier transform. Since it's unitary, its inverse is basically itself. Remember, homework. And then perform the measurement, and the math says, so the measurement, the result of the first n qubits will be the superposition of states with complex coefficient Cx. And then performing a measurement means one of these states will collapse to one of these states with certain probabilities described by the square of this complex number Cx squared. Yes. So every possible x is possible, but some are more likely and some are less likely. And then the math, which I'm going to skip, says that the one we're interested in y. So in this sum with x, we're interested in the term where x is equal to y, one term in this exponential sum. And it turns out that mathematically this is the most likely one. This is the one where the coefficient C is largest, and it's actually 4 larger or equal to 4 over pi squared. Now when you do the math, that's something like 0.4, 40%. So with a little bit over 40%, our measurement will yield the desired approximation to the phase. That's why I said the goal is to not to compute the phase, but to approximate it, at least with high probability. Okay. Now 40%, is that a high probability? Well, yes and no. In chapter 5, we will see that it's this general technique of so-called probability amplification. By repeatedly running that, such a randomized algorithm, we can blow up the probability or decrease the error probability arbitrarily small. So 40% by itself is not good enough, but if we do it twice, then it's already like something like 70%. If we do it 3 times, it's 90%, and so on. So for that purpose, remember, we keep repeating things whenever something goes wrong all the time. In Shor's algorithm, when something goes wrong, try again. Here, when something goes wrong, try again. Probability amplification. So yeah, I'm not going to explain to you the math, but this is the fact that we want to keep in mind. And this is the solution to the quantum phase estimation problem. First Hadamard, or the first n qubits, then these controlled powers of u, all possible powers of u, controlled by the value of the first n qubits, then inverse Fourier transform, and then measurement. That's a circuit. And as I said, the math promises that this works. Now the remaining obstacle is that these controlled powers of u are exponentially large. As I said, everything we do here is exponentially large. Input vector states have exponential dimension. Therefore, also the unitary transforms are exponential size. But at least for the Fourier transform, we were able to express it, although exponentially large, using only polynomial many tensor product. Now, how about this V? And we express V in polynomial size? In general, not. So this is the exponential size. V has exponential size in general. But for some u, we can do better. We can make V have polynomial size. And the u that we have been considering all the time for Shor's algorithm is luckily of this form. Then the idea is basically repeated squaring, but now in the quantum setting. Remember, what do we do in repeated squaring in order to calculate the case power of u? We calculate u squared, u to the 4th, u to the 8th, 16, and so on, and ignore all the things in between. That's already an improvement, right? Before we would need u squared, u cubed, 3rd, 4th, 5th, 6th, and so on, exponentially many powers. Now we need only linearly powers, u squared to the 4th, to the 8th, to the 16, and so on. Larger and larger gaps in between. But the exponents still become exponentially large, right? The last one is still going to be u to the 2 to the n, or 2 to the n minus 1. And this is where the second trick comes in. So the first trick is repeated squaring carried over to the setting. And the other trick is Yeah, here you see the V as a circuit. So here we have this n0 input qubits, n-fold Hadamard transform. Here we have the promised eigenvector psi, which is an m qubit vector. Here, repeated square, we apply u to the first, right, to the 0, u squared, u to the fourth, u to the 8, u to the 2 to the n minus 1. That's the repeated squaring. So now you see that this involves only a polynomial number of powers of u, but still u up to exponential power. And if we know nothing about u, the only thing we can do here is u times u times u times u exponentially often. But here we do know something about u. Remember, this is the u we used. Take basis vector, which is a binary of L, and output the basis vector, which is binary L times A modulo X. So what is u to the k, or u to the 2 to the k? That takes the basis vector L binary to the basis vector L times A to the k, or 2 to the k, modulo X. And this is, by repeated squaring, again something we can write more efficiently than just writing u times u times u. Maybe by multiplying L with A squared, then taking the remainder modulo X, then multiplying that again with A squared, taking the remainder. So repeatedly taking this remainder, modular repeated squaring, we can express this exponential power using only polynomial number of circuits, but different circuits. It's not u, but it's a different one. So, yeah, this is, remember my pedagogical concept, start easy and then become more and more difficult. This is a most difficult part. So if you've got lost here, this is the point to resume your attention. Of course, the take-home message is that this particular form of u, the controlled powers, can be implemented only using only polynomial size. And therefore, the quantum phase estimation meta circuit that we discussed on the previous slide, this one, also can be represented in polynomial size. There's this n-fold Hadamard gate, then there's this control powers, which we just saw, because of the particular form of u can be done, not in general, that's why it's the general quantum phase estimation problem cannot be solved efficiently, but only for very specific u's, and here we have such a u. And the inverse quantum Fourier transform also. So that's basically the end. Now you have seen Shor's algorithm. No, of course you haven't, right? Because again, I've repeatedly used all these abstraction concepts, right? So I presented you the classical hybrid Shor algorithm, making subroutine calls in order to determine the order Then how to determine the order using this quantum phase estimation, approximation with high probability, and how to solve the quantum. Putting all these things together, that's still a huge endeavor. And implementing them, that's even more challenging, right? With all this noise and heat sources that destroy the superpositions, the entanglements. That's why even 30 years after Peter Shor presented the algorithm, it's still not running in practice. But that's not our concern. Our concern is we've learned about quantum computing from experimental physical evidence, mathematical background, quantum states, quantum operators, pure states versus mixed states, entanglement, superposition, Einstein, Podolsky, Rosen, thought experiment. Einstein tried to discredit quantum mechanics as an inherently random, non-deterministic theory, but it turns out it's just nature is that way, whether we like it or not. And we talked about qubits, first like with light, polarized light, linearly, vertically, circularly, left, right. Then as qubit register, we're using, for example, ion traps where spin up and down. Then primitive gates, one qubit gates like the Pauli or the Hadamard, two qubit gates like the controlled knot or tensor product of Hadamard. Combining these primitive gates leads to quantum circuits. Sequential combination corresponds to multiplication of unitary matrix. Concurrent corresponds to tensor product. In quantum parallelism, how it is very different from classical parallelism. People keep confusing that, so I hope to use you as multipliers when you talk to people on the street. This is what quantum parallelism is about and not something else that is. Honestly, I understand why it's so easy to confuse. Then we talked about quantum phase estimation as a problem, meta problem, and the quantum phase estimation solving meta circuit, which involves U and its powers. And because of the special form of U, how it is invoked in Shor's algorithm, we can implement this actually in polynomial size. And that's the end of chapter 11.